Hello friends, this is another lecture of EMT for BSc and MSc students. Today we're going to discuss about Gauss transformation. Here we're going to get Lorentz transformation and Coulomb Gauss, Lorentz Gauss and Coulomb Gauss. So before you watch this video, for better understanding, I would like to suggest please do watch lecture number 4 and lecture number 5. Okay, lecture number 4 and lecture number 5 of EMT. I have given the links in the description box. Okay, and one more important thing, if you know someone who is going to appear ACE's final examination under Assam Higher Secondary Education Council this year in 2025, so please inform that from the next week I'm gonna solve previous year's questions of ACE's final examination under Assam Higher Secondary Education Council. So if you know someone, maybe your cousin or brothers and sisters, please do inform them. Okay, and so let's start. And before that, please do subscribe the channel if you are new, and do hit the thumbs up button. Also hit the bell icon so that you get notified when new video will be uploaded. And if you want to follow me on Insta, this is my Insta ID, OJHALAKHYAJIT123. This is my Insta ID, so you can follow me on Insta. So now let's start. What is Gauss transformation? Now you see in lecture number 5, link of the lecture or lecture 5 is given in the description box. That we have already discussed that how these two, magnetic field and electric field, these are invariant under Gauss transformation, and we have already discussed that. We also know that we have already discussed in earlier videos that we know that magnetic field B, it can be expressed in terms of curl of vector potential A, and electric field, it can be expressed in terms of divergence of scalar potential phi. So we know those things, and if you don't know, then what's the video which is I have given the link of that video also. I have forgot in which lecture I have discussed about this. I think I have discussed these things in lecture number 4. Okay, lecture number 4. I have given the link of lecture number 4 and 5. Okay, 4 and 5. Please do watch those two videos. Okay, I have given the links of these two lectures. Okay, now you see, let me write here. Let us suppose A and phi, these are respectively be suppose vector potential and scalar potential, right? such that this vector potential A, let me write here first, such that the vector potential A changes to A dash, and the scalar potential phi changes to phi dash. So, as A dash is equal to A vector plus divergence of phi. Okay, divergence of phi. And similarly, this scalar potential phi dash also related with can be related with this phi minus del psi by del t. Okay, where this psi is called any arbitrary function, scalar function called Gauss function. Psi is any arbitrary scalar function called Gauss function, right? Now you see here, this let me take this is equation number 1 and this is equation number 2, right? Now you see, if any physical quantity, for example magnetic field and electric field, right, that can be expressed in terms of this vector and scalar potential respectively, and remains unaffected by this transformation, right? When this A and this phi transform to A dash and phi dash remain unaffected, these two quantity suppose remain unaffected, okay, then these two transformations are said to be Gauss transformation, okay, right? So now you see, so what we're going to write here, if any physical law that can be expressed in terms of the electromagnetic potentials A vector and phi, okay, remains unaffected by the transformation equations, by the transformation equations, equation number 1 and 2, equation number 1 and equation number 2, right? Then these transformation equations are said to be Gauss transformation. These transformation equations are said to be, let me write here, are said to be Gauss transformation. Gauss transformation. Right? So hope you have understood this, what is Gauss transformation, right? I have already shown that this electric field and the magnetic field B and electric field E are invariant under this transformation, already discussed in lecture number 5, link is in the description box, okay? And why and how we can express this field in terms of this scalar and vector potentials, I have already discussed in lecture number 4. That lecture is also in the description box, link of that lecture. So watch those two videos to better understand this. Okay, now let me take a new slide and let me discuss about let me explain about Lorentz Gauss transformation, Lorentz Gauss condition. So now let's discuss about Lorentz Gauss. Now you see, I hope you know the Maxwell equations in terms of vector and scalar potential. So let me write those two equations. Maxwell's field equations in terms of electromagnetic potentials, that means in terms of A and phi. This is one and this is the next one. Okay, I have taken equation number 3 and 4. Okay, so these are the Maxwell equations in terms of vector and scalar potentials. Now you see, in both equations we have seen both scalar and vector potentials. So if we want to represent them either in terms of only scalar or in terms of only vector potentials, then what we have to apply? We have to apply the Lorentz condition. Okay, when the vector and scalar potentials satisfy the condition, this condition here you can see, which is called Lorentz Gauss condition, then the Gauss is called, Gauss means the the scalar and vector potential that we have considered, okay, that potentials is nothing but Gauss. The term to represent those two, I have used the term Gauss, okay. Then Gauss is known as Lorentz Gauss, okay. Now you see, if you use this condition here, then this term gonna be equal to 0, and here what happens, you can see this term can be replaced by minus of this, negative of this, right? So that means, let me take a new slide. Now you see, if you apply this condition in equation number 3, then this equation number 3 will be, of this form. Sorry, let me write here equation number 3. So this part will be 0, so we can take this part, right, only we're gonna take this part is equal to, then right hand side is equal to minus mu naught j, minus mu naught j. So that's what we're gonna have, right? Then you see, this can be written in this term as well. So here you see, this equation consists only the vector potential, right? Then this equation can be written in this form as well, as using the box operator. That means the de-alumbration operator, also known as box operator. It can be written in this form, in this way. Right? Where this box operator or de-alumbration operator is nothing but del square minus mu naught epsilon naught second order differential coefficient with respect to time t. Right. This is de-alumbration operator, or simply known as box operator, right? And you see, the equation number 4, this equation number 4, let me copy this equation number 4, okay. You see, this equation can be written in this form. Just let me write this way. This equation can be written in this form. Simply we can write this way, right? Sorry, minus epsilon naught and mu naught del 2 phi by del t2 minus then del t of divergence of A, then minus, let me write here plus, and then here it will be also plus mu naught epsilon naught, so del phi by del t. We can write this way, minus epsilon, right? We can write this way. So if you open the bracket, then again you're gonna get this term del t of divergence of A plus mu naught epsilon naught second order derivative, partial derivative of phi with respect to t, and this term will be cancelled by this one. Then again you're gonna get this equation, right? So hope you have understood this. Now you see, if you apply the Lorentz Gauss condition, that means this one, if you apply that, then this term gonna be equal to 0, right? Then this equation will be of this form. Then the equation will be of this form, right? So hope you have understood this, okay? If that is the case, right, if that is the case, then you see, we can write this using the box operator in this way, minus this is equal to minus rho by epsilon naught. That's how we can write. Okay, so hope you have understood this. Okay, now you see, what is the importance of this Lorentz Gauss? using the Lorentz gauge, we have uncoupled these two, vector and scalar potential, from these two equations, right? Hope you have understood this. So let me write the importance of Lorentz gauge. So here is the importance. Okay, it is used to uncouple the Maxwell's equations, wave equations for vector and scalar potentials respectively, A and phi, right? So now let us discuss about Coulomb gauge, okay, which is also known as transverse gauge. Now let's discuss about Coulomb gauge. Now you see this equation number 4, just wait, give me a second. This equation, you can see the equation number 4, this equation. Okay, let me copy this equation. Now Coulomb gauge condition is this: divergence of vector A is equal to 0. This is Coulomb gauge equation. Okay. This is Coulomb gauge equation. This was equation number 4. Okay. Now if you apply this condition, Coulomb gauge condition, then equation number 4 will be of this form. Which is nothing but Poisson's equation. Poisson's equation, right? Now you see, using the same condition, the equation number 3, this equation number 3, let me copy this equation number 3, this one, equation number 3, this equation, here you see. So let me write this equation. This equation number 3, if we use the, here let me write it, applying Coulomb gauge condition, this equation number 4 becomes this, and equation number 3 and equation number 3 becomes this part gonna be equal to 0, right? This part is equal to 0. So here we're gonna write this equation turns reduced to is in this form, reduced to this form. Okay, right? So hope you will understood this. So now let me clean this too. Okay, just you need to note this. So okay, so this is the Coulomb gauge condition. So its importance of Coulomb gauge is that it simplifies, you can write it simplifies equations, separates scalar and vector potentials, scalar and vector potentials, right? So hope you have understood this. So thank you for watching. See you in the next video.